Good. So, as you'll recall, last time we were discussing, can I hear you? No, nope. But I've muted everyone, so I'll do it again just in case other people's mics are distracting others of you. But I can't hear you guys at all. So you can say whatever dirty words you wish about me and my teaching, but probably you shouldn't. Okay. So last time we covered the basics of electrophilic aromatic substitution. We talked about what the mechanisms of those reactions are. They're really all pretty much the same. They only differ in the details of which exact electrophilic species is undergoing substitution on the aromatic ring. But there's a problem. We only discussed the reaction of unsubstituted benzene. What happens if there's already another substituent group or multiple substituent groups on the aromatic ring? And we're going to go through that little by little, step by step. I'm pointing you here to a table and a figure in your book which carries those answers. That's how you answer those questions. If there's already a substituent group. Just to give you an idea of what I mean by the issue itself, here we have not just unsubstituted benzene, but methoxybenzene, which is also called anisole. That's the common name for this guy, anisole, anisole. So if we nitrate it, this part of the question is something we know already from last time. We know that this is going to put an NO2 group on the ring, right? It's going to replace a hydrogen with a nitro group. But which hydrogen? This one, this one, this one. Well, those two are the same as each other. Those two are both ortho to the methoxy group. These two are both meta, and then you have the unique paraproton. So which is it? Or likewise, if instead of a methoxy group already present, as in anisole, let's say we use nitrobenzene. Well, this is going to put another nitro group on there. But where? Will it be ortho to the pre-existing nitro group, or meta to it, or para to it? And so what you first of all need to know is whether any given group is ortho-para directing or meta directing. And then there's also this issue of activating versus deactivating, for which, by the way, there's a lot of overlap. There's only one kind of weird one that's right in the middle. Essentially, all ortho-para directing groups are going to be activating, meaning they make the reaction faster, other things being equal. With one exception, your meta-directing groups, no, I guess I have it backwards. All ortho-para directing groups will be activating except for one, and we'll get to that. That's the weird one that's right in the middle. And all meta-directing groups, without exception, will be deactivating. So we'll get to what all that means, one at a time, step by step. So if we, the simple-minded way of going about this, which we should start with, if we look at our information in the book there, we find that methoxy and other alkoxy groups are all ortho-para directing. So that means that we can predict that the products of this reaction will have the new nitro group. See, I guess I'll need a little more space here, but it will have the new nitro group be ortho or para to the pre-existing methoxy group. So one of the products is going to have the nitro group be ortho to the pre-existing methoxy group. Of course, you could also put it up here. It's the same thing, right? The molecule's flat. You're just flipping it over. It's the same thing. And the other product will have the nitro group para to the pre-existing methoxy group. And so what you put down in answer to the question, as always, depends on how it's phrased. If the question asks for what are the products, any and all products, well, you'll need to put both of them. But if the question asks for the major product, and I'll again remind you, I put old exams on eCampus, but if it asks for the major product, well, if you were to take a wild guess which of these there's more of than the other, I think you would all guess that the para product will be the major product because there's more room for it out here. Putting it next to the methoxy group, there's steric crowding there. So even though there's two ortho positions, in general, you can expect that the major product is going to be the para product. And so this is going to be the major product. So again, what you put down depends on how the question's phrased. But in general, you can expect, without exception, you can expect the major product to be the para product. At least I would. Yes, there are some weird cases where the ortho product is actually the major one. I do not expect you to memorize those. And just as I say over here in those tables, of course you don't have to memorize any exact percentages. Now, their major and minor mean thermodynamic and kinetic. Actually, I don't know. It probably depends on the exact situation. But not every major minor means thermo and kinetic. That they are not necessarily related. But that's actually a good question. I haven't really thought about that. But I think the one-word answer to your question is no. We just have major products and minor products, and the only issue is where is there more room for the new incoming group. And so I think the para product, it's reasonable to expect that the para product will always be the major product. Always, no exceptions. Yes, there probably in real life are exceptions. I don't expect you to memorize any of them. So again, what you put down depends on what the question says. Owl might say, draw all products, in which case you'd put both of them. And if Owl instead says, put the major product, well then you'd put the para product. Usually we're interested in the major product, so I think it's altogether reasonable, unless it specifically says otherwise, to put the major product. And that would be certainly what I would expect to be the case. Apart from other information, which in general we don't have, we can expect in the case of benzene with an ortho-para-directing substituent on it, that the para product will be the major product. That's what I would put. That's what I would always say. Meanwhile, what about this guy? Well, again, if we look at our table, we find that the pre-existing nitro group, again, don't confuse the pre-existing nitro group with the nitro group that we're putting on. It's always affected by whatever is already on the benzene ring. So direction of substitution always depends on the pre-existing group, not on the group that we're putting on. So that's something you have to be very clear about. It depends on what's there already, not on what we're putting on. But if we look it up, we find that the nitro group is meta-directing. So that means we can reasonably expect that the major product is going to have the new nitro group meta to the pre-existing one. Looks like I've confused it. NO2. Good. And also notice ChemDraw did it automatically. Notice how we're writing O2N instead of NO2 on the left side of the molecule. That shows that we understand that it's the nitrogen that's attached to the carbon, not one of the oxygens. So I think that's the best way to draw it when the nitro group is on the left side of the molecule. Just like if there's a carboxylic acid group, we don't write CO2H, we write HO2C, right? It's the same type of thing. With nitrogen, we can be picky. Of course, something like methyl, CH3, H3C, I don't really care. We have to be a little bit flexible with carbon because there's 4 bonds, and that makes it hard to linearize, hard to show in on one line with condensing it. So I would expect that to be not only the major product, but even the exclusive product. I would expect we would get at most a couple % of the other two. And the major product by far with an ortho-para-directing group, I would in general expect to be the para product, because there's more room to put the new group out there. So that's the first thing you need to know. You need to be really clear on the difference between the group that's already there and the group that you're putting on. And it's the group that's already there that determines where the new group goes. So ortho-para-directing groups will put the new group into the ortho and para positions, and I would expect the para substituted one to be the major product, and meta-directing groups will put the incoming group in the meta position to the pre-existing group. And Bella's back. No problem. Busy. Goodness. Okay. So what about the mechanism? What do you need to know about the mechanism? Well, you already know the mechanism. The mechanism is identical to what you've already learned. There's nothing new that you need to know. If I were to draw the mechanism, for example, of aniline reacting with nitrobenzene, again, in the class notes, I've been very clear on what you have to put for full credit. But so how can you tell if the molecule is parameta or ortho based in the pre-existing group? Well, what you do is you look at these tables and these figures. They tell you which groups are ortho-para-directing and which groups are meta-directing. So if you look up for methoxy, you'll see that it says that alkoxy groups in general are ortho-para-directing. Well, you'll remember that the exam's open book. So I don't know that I'd recommend you memorize it anyway, but the exam's open book, so that's not even an issue. But I would hope that you'll have practiced enough that you're not simply looking at it all the time. You'll save yourself a lot of time and therefore a lot of points if you kind of have the idea of which groups are ortho-para-directing and which groups are meta-directing. It's not at random. I think you'll find that there's a pattern. I think you'll find, let me even write this down for you. Here's what I really expect you to know. In general, the ortho-para directing groups, which are also, by and large, the activating groups, are electron-rich, or electron donating, if you will. You can think of it either way. And the meta-directing groups are electron withdrawing. And I don't want you memorizing those sentences. I expect you to be able to look at these and tell which is the case. So how do we know that the methoxy, and along with it, other alkoxy groups are electron-rich or electron-donating? Well, we've got these two big fat lone pairs there on that oxygen. That's going to donate electron density into the ring. And we'll talk about that. I will show you exactly what you need to know about that. We'll get to that. I already have the structures there in your class notes. But based on that, I don't think anyone here would be surprised at alkoxy groups being electron donating. And what we're going to talk about in a little bit is exactly why their being electron donating makes them ortho and para directing. I think in all of them, you'll find there's either lone pairs on that atom that's attached to carbon, or at the very least, you have an electron-rich alkyl group, something like that. Alkyl groups don't have lone pairs on the carbon, right? So they're not electron donating in that sense. But compared to a hydrogen, like let's say we had CH3, we had methyl or ethyl or isopropyl or something, there's a lot more electrons around that alkyl group than there are around a hydrogen. So I don't think anyone would be surprised that alkyl groups are electron donating. Meanwhile, how do we know that the nitro group and others of these electron withdrawing groups, how do we know that those are electron withdrawing? Well, we know that based on the structure. And that's why I said the other day that you need to know the structure of the nitro group. Even if you're not asked directly, what is the structure of the nitro group? You need to know it in order to understand what's going on here. And we went over that. We said that the Nitro group is a resonance stabilized species. And there will always be a plus charge on nitrogen. That can't be avoided. And let me just try to get these out of the way a little bit better. Remember us discussing this the other day, what the structure of NO2 is? And again, whether you'll lose points if you write NO2 or not is not the issue here. It's understanding what's going on. The wording of the question should make that clear anyway. But now if we look at the nitro group, yes, you do have these oxygens there too, but directly attached to the benzene ring, and therefore much closer to the benzene ring than either of those oxygens, directly attached to the benzene ring is a nitrogen with a plus charge. And so that's why that group is electron withdrawing. It's because you've got a positively charged atom directly attached to the benzene ring. So that's going to suck electron density towards it. And if you look at the other meta-directing groups, I think you'll see that they're largely carbonyl groups with a C double bond O directly attached to the benzene ring. And so how come carbonyl groups like, let's say, I'm trying not to jump around too much, but I'm also trying to show you enough that, that you can buy into why the electron donating groups are electron donating and why the electron withdrawing groups are electron withdrawing. So if we considered, for example, this compound, acetophenone, we got a carbonyl group attached to the benzene ring. And as you may recall, carbonyl groups are themselves resonance stabilized such that there is a partial plus charge, rat. There is a partial plus charge. I hope this is helpful. I'm trying to give you visual aids on why these things are the way they are. But if you'll recall, you can also write resonance forms such as this. That's a minor resonance contributor to any carbonyl group, not just this one. And by the way, welcome to pretty much all of the chapters from like 19 to 23 or thereabouts, where we'll be covering carbonyl chemistry in detail. But once again, you've got a partial plus charge on this carbon. It's not a full plus charge, but it is a partial plus charge. So no wonder this is withdrawing electron density from the benzene ring. So understanding those things will help you to understand that table, because I guarantee you, if you go into the exam not understanding anything and expecting that the table will save you, it won't. You need to understand this. And so that's what we're going to spend most of the time talking about today, is why the ortho-directing groups or ortho-para-directing groups are ortho-para-directing, and why the meta-directing groups are meta-directing. In terms of the mechanism of the reaction, there is nothing else you need to know. You already know everything necessary in terms of the mechanism of the reaction. You just need to make sure that if you're asked, for instance, how we get from this compound to the para product, you just need to be sure that you show the group adding to the para position. And so let's say we were asked for the mechanism of this compound going to the para product. Oh, I forgot to put in the actual reaction. Nitric acid and sulfuric acid. Oops, did that wrong. Well, again, I will put down whatever I need to put down based on what the notes say I need to put down. I've made that very clear in the class notes, and I don't wish to go over that in detail again. but you'll recall that addition of the nitro group involves formation of the nitronium ion, NO2+. And so we will show whatever the class notes say we need to show, but at some point, we generate this nitronium ion, and the mechanism of the reaction involves addition of the nitro or the nitronium ion to the benzene ring using one of those pi bonds, or the electrons in the pi bond, even though we understand they aren't really localized like that. But it involves one of these pi bonds swinging out, attacking the nitrogen and breaking one of the nitrogen-oxygen pi bonds. We just need to be sure we swing out the right one. In this case, we want to show that we're forming a bond between the paracarbon and the nitrogen. And that's one way of doing it. It doesn't have to look exactly like that, of course. By the way, if you want to review how to know whether you're drawing arrows right or not, I would suggest you look back at my class notes for chapter 6. I have a handout there that goes over that shows you exactly how to know whether you're drawing arrows correctly or not. Just some general ideas on that. Do you have to? Well, again, I'm not going to talk about that because it says in the class notes. For all of the actual reactions, it says here what you need to show. So I'm not going to go over all that in detail. I'm just showing you what that part of the mechanism looks like. So anyway, once you've done that, you've got your sigma complex, as we call it. So that would look something like this. We'll have our hydrogen, we'll have our nitro group, and we'll of course have a plus charge now on the aromatic ring. And that's not the only way to draw the mechanism. Oh crap, what have I done? Hold on. First of all, I forgot to put the nitro group over here. This requires being a bit clever. Give me just a moment. This is what we call a nice save. There we go. Now we're in good shape. So we do get this intermediate, and then we need to show removal of the proton to move the electrons in the carbon-hydrogen bond back into the aromatic ring. And again, I look around for anything that I can use as a base, and there really is nothing. You know, I can't use water because there effectively is none. Really, the only one I've got is the conjugate base of sulfuric acid, which is the bisulfate ion. And a terrible base it most certainly is, but there literally is nothing else. We have no choice. Well, I'll just go like this. All of the other atoms have a formal charge of 0, so I won't go nuts with electrons. We do have to show those, right? Because that one's got a formal charge on it. And so this is really our only choice for what we use to pull off that proton. So again, the class notes are very explicit about what you have to show. But when it comes to the part of the mechanism that involves putting the nitro group on, that's the way we would do that. So it's the same mechanism. The mechanism hasn't changed at all. We're just showing that this is really beginning to be a pain. Let's see. I'll just put it over there. Oh, okay. Anyways, so that's how we would show those two steps. It's the same mechanism. You don't have to learn anything new about the mechanism because it's the same. We just need to be careful to show that it's getting attached to the right place. So as far as that goes, there's nothing new to learn. We already know these mechanisms. In principle, we went over it last time. So that leaves only the question of why. Why the ortho-para-directing groups are ortho-para-directing, why the meta-directing groups are meta-directing. And as I said, all of the ortho-para-directing groups, save one, are also activating. And what that means is that other things being equal, the reaction is faster than with just unsubstituted benzene. And again, I would never ask you to speculate with exact numbers as to how much faster this one is than that one. There's no way you can know that in any given situation unless you have the data in front of you, or you're doing the experiment yourself. The exception is the halogens. The halogens are ortho-para-directing but deactivating. They're the only ones. What that means is if instead of methoxy, we had chlorine or bromine or iodine, or even fluorine, I guess, then we would still get the major product being the para-substituted product. There'd probably be a little bit of ortho as well, and the mechanism would again be exactly the same, except there would be the halogen attached instead of the methoxy attached. The only difference is that reaction we would expect to be slower than the reaction with just unsubstituted benzene. And then all of the meta-substituted, all of the meta-directing groups are now, without exception, deactivating, meaning all of those reactions would be slower than the reaction with just unsubstituted benzene. And again, I'm not interested in the numbers. They have them in the book in case you're curious, but I'm not interested in being at all quantitative about that. So if we understand the meaning of what those tables and diagrams in the book are showing you, it's that if we have a pre-existing ortho-para-directing group on the benzene ring and we do any of the reactions we talked about, not just nitration, if we did halogenation or one of the Friedel-Crafts reactions, let's say, or any of the other ones that we talked about the last time, the reaction will proceed with exactly the same mechanism to give as the major product the para-substituted product. And if we're asked instead, what are all the products? Well, it would be both ortho and para, would be all of the products. And again, if there's a meta-directing group already on the ring, then we get the meta-substituted product as the major product. So we've got to get that down very clearly. So just having the table in front of you is not going to save you here. Oh, I thought of something else. Since I mentioned this to my 227 students, it just popped into my head. Do you really want to know what I suggest you do before the next exam that I think will both save you a lot of time and give you something to look at during the exam? Make a cheat sheet. In fact, I like this idea so much, I may just in future just say you may use a cheat sheet. So, you know, one page or both sides of one page, make a cheat sheet. Summarize everything. Try not to write so small that you need a magnifying glass, you know. But honestly, that will help you so much in terms of organizing the material, because I really think a lot of people are going to try to have the book open and the notes open and this open and that, you know, you're going to drive yourself crazy. So try to come up with something that, you know, you reasonably think is going to help you 90% of the time. I actually, in terms of strategy, would recommend that you try to do as much of the exam as you can without looking at anything, just to save yourself time. But I think if you make your own cheat sheet, that's going to be so helpful to you when you're studying. I bet you learn a bunch just making it. So I recommend that that you make a cheat sheet. I think that's going to save you a bunch of time. Good. So with that appeal over, let's then address the question of why ortho-para-directing groups are ortho-para-directing and why meta-directing groups are meta-directing. I was hoping to start to get into multiple substituent effects, With only 20 minutes left, I don't think we're going to do that, since I'd like to go over two different ways of explaining why meta-directing groups are meta-directing and why ortho-para-directing groups are ortho-para-directing. And the reason I want to do that is I don't know which is going to work best for each individual student's learning style. They're both correct, and they both explain it. So that being said, just let me look ahead about multiple substituent effects a little bit. In other words, what if there's two groups in the benzene ring? What if there's three? If you look ahead in my class notes, I think you'll see I bring you through that step by step. I've broken that information down for you in a way that I think will make it very easy to follow and very easy to make a decision as to what the major product's going to be, if, let's say, there's two groups on benzene before you start. Good, so that being said, let me see if I can't move this down here. Goodness, why does that look so weird? I think I'm really only going to be using, at least for now, I'm just going to be using the Word document. Good, so let's go back to the reaction we were talking about. Here is the nitration of anisole. And again, we're starting here at the step where we're just adding the nitronium ion. And let's look carefully at the carbocation intermediate. By the way, I should mention, this is not the only correct way to draw that mechanism. You can also show this pi bond shifting over here, which would give you this structure. Or you can even show the methoxy donating an electron pair in from the oxygen going, and so you'll get this structure. So all four of these structures play a role in the overall molecular orbital picture for that intermediate. So they all play a role. It's a resonance stabilized species. And so what we find is that there's always going to be at least these three resonance forms for sure. Now, true, if instead of methoxy we had methyl, well, we wouldn't have this fourth resonance form. But we'll always have at least these three. And the very least we can say is that we find a resonance structure that puts the plus charge right next to an electron-rich atom, even if this were just CH3 instead of OCH3. That would be true. The plus charge is going to be next to our electron-rich atom. So this is a well-stabilized carbocation. And in the case where we have, let's say, an oxygen or nitrogen here, well, we have a fourth resonance form that actually takes the plus charge out of the ring and puts it onto that heteroatom, so that there's now four rather than three atoms that are sharing the plus charge. And so, although this is a carbocation, as carbocations go, this is a fairly well-stabilized one. So no wonder this would rather attack from the para position, because the intermediate that you get has four different resonance forms, any of which you could draw, by the way. Right? I think we've gone over the rule of what you have to put when you've got a resonance stabilized species in a mechanism. And the answer is you can use any of the resonance forms, unless it specifically says to draw all of them. Any one of them is fine. You can draw whichever of these resonance forms you like, and you can draw a correct mechanism based on that. So there's no one of them that's any more correct than any other. So the reason that we get attacked from the para position is the intermediate that we then get is especially well stabilized. And something that would be worth your time, that would not be a waste of your time, would be considering what would happen if we get attacked from the ortho position. I think you'll find the exact same thing, that you get an especially well stabilized intermediate. In the case of this one, you've got four resonance contributors. Of course, I think you would get less attack from the ortho position simply because the methoxy group's in the way. Might as well put it out where the group has more room. What though if we did get attack from the meta position? I mean, we can show that. It certainly could happen, you know, a few times out of 1,000. But then what we wind up getting is a particularly bad intermediate in terms of its stabilization. We get only 3 resonance forms, and in no case are we putting that plus charge onto this especially well stabilized position, owing to being next to an electron-rich atom. We're putting the plus charge in all of the wrong places, where there's no way we can stabilize it by this electron-rich atom. So yes, you get a resonance stabilized species, but nowhere near as well stabilized as this one, where we can certainly put the plus charge right next to the electron-rich atom. And in the cases where that atom also has non-bonding electrons, we can even use a non-bonding electron pair to stabilize that plus charge further by sharing it not only amongst those 3 carbon atoms, but also on that heteroatom. And you'll see that when there's an oxygen or nitrogen attached directly to the aromatic ring. So in comparison, I think we have to agree this intermediate is much better than this intermediate. And so that's one reason why attack from the para position is so favored over attack from the meta position. And again, this is all already in your class notes. I've given you all of these structures already. So the idea is somewhat subtle, but I think it's one you can handle. The reason we prefer attack from the para position with an ortho-para directing group is because we get an intermediate that's more stabilized as compared to when we attack from the meta position. And this is just one way of explaining it. Dr. Pennington, when he goes over this material, he also gives an explanation. Actually, I think he gives a different explanation from this one, which is equally correct and which might be easier for some of you to understand. So we'll try to go over that as well. What about nitro directing groups? I'm sorry, meta directing groups like nitro. Well, let's compare what happens when we've got nitrobenzene and we attack the nitronium ion from the para position, which is not the way we would expect the reaction to go. Well, we get a resonance stabilized intermediate, but there's one resonance contributor that's especially bad. It's putting the plus charge right next to that electron withdrawing nitro group. So this is a very destabilized intermediate. Yes, it's resonance stabilized, but we're putting plus charge in the worst possible place to put it, right next to that electron withdrawing nitro group. If instead we attack from the meta, I should also mention, if you also see what would happen if you attack from the ortho position, I predict you'll find something very similar, that one of the 3 resonance forms is particularly bad. As long as we attack from the meta position, then at least we're never putting any partial plus charge right next to that nitro group. At least we're keeping the plus charge on the 3 carbon atoms that aren't especially stripped of electron density by that electron withdrawing nitro group. And we would find the same thing if this nitro group were an aldehyde or carboxylic acid or ester group or ketone, let's say. At least we wouldn't be putting the plus charge right next to the electron withdrawing group. So it's a little bit subtle, whereas with the ortho-para directing groups, when we look at both possibilities, we find that one intermediate is especially stabilized as opposed to the other. And so one of them looks much better than the other. So no wonder we get attack from the para position. Preferentially, you get a much better stabilized intermediate. Let's say with meta directing groups, the argument is a little more subtle. What we find is that both of them are bad, but one of them is significantly less bad, because at least we're never putting the plus charge right next to our electron withdrawing group. And so we prefer the one that's less bad. And it turns out that that's going to be attack from the meta position. So this is one way of explaining why ortho-para directing groups are ortho-para directing and why meta directing groups are meta directing. In the case of the ortho-para directing groups, we find that if we compare the 2 possibilities, ortho-para substitution versus meta substitution, it's easy to see why ortho or para substitution is very well favored over meta substitution, because we get a nicely stabilized Is it still possible for a meta-directing benzene? Yeah, the one-word answer to your question is absolutely. And you probably will get some, 0.3% or something. Probably not even enough to detect. But you will get some of these. It's not the case that every single molecule does this. Remember, whenever we're drawing a mechanism, we're not meaning to imply that every single molecule does that. But it's safe to say that most of them do. In general, that's what's going to happen. Likewise, you will get some teeny amount of the meta-substituted product with an orthopower-directing substituent. But in general, I would expect it not even to be enough to detect, probably less than 1%. And certainly if you're asked what the major product is, with a meta-directing group, that's clear. You'll pick the meta-substituted product. And with an orthopower-directing group, if you're asked for the major product, I would always predict the para product would be the major product. If instead it says to put all of them, then you'll put both ortho and para. But this is an explanation of why the orthopower-directing groups are orthopower-directing and why the meta-directing groups are meta-directing, based on the stability of the intermediate. But that's not the only way to explain it. So let me now, where is it? Let me now minimize this and show you another way of considering that. Let me open my ChemDraw here. That's equally correct, and for all I know, might work better for some of you. You can also make the same type of argument based just on the starting material. So let's consider again, I'm just using a methoxy group as an example, but I could use any of those orthopower-directing groups. I think you will find, if we consider other resonance forms, that there's quite a few others. And I mean, of course, apart from the trivial ones where we just put the other Kekule form, though that's certainly there. But I think if you look at this carefully, you'll see there's other resonance contributors, at least 3 good other resonance contributors. One of them looks like this. And there's another one that puts the minus charge over here. And still, of course, the plus charge on oxygen. And we'll also have now our minus charge, over there. This is how Dr. Pennington explains it to his class. And of course, he didn't make this up, just as I didn't make up the other thing. But I think it's an equally valuable way to understand it. So that's another resonance form. And then there's one last one that has extra electron density on this carbon over here. And of course, all of those are relatively minor contributors compared to the one with no charge separation. But if you look at those 3 structures, and you ask, where's the extra electron density? Well, it's in the 2 ortho positions and in the para position. No wonder the compound likes to react from those 3 carbons. Those are the ones that have extra electron. Ooh, do I have one with 5 bonds? That's a problem. Thank you. Yes, we do not violate the octet rule. Thank you, that's more better. Aren't the 2nd and 4th one? No, because remember, with resonance forms, you're not allowed to move any atoms or turn the molecule. You're only allowed to consider different ways to put in the electrons. So those 2 are not the same. They're equivalent, certainly, but they're not the same. You're not allowed to turn the molecule over. Remember, with resonance, you have to leave all of the atomic nuclei in the same place. So that being said, there's others, by the way, too. I think we would probably find others. But I mean, of course, there's at least one more for sure. You could also put the other Kekule structure with the double bonds in the other place. So certainly that's there too. But these three structures explain why a group like methoxy is orthopara-directing. Look at where the extra electron density is. Remember what we're expecting the benzene ring to do in an electrophilic aromatic substitution. We're expecting the benzene ring to act as a nucleophile. If we were expecting the benzene ring to give up an electron pair and donate that electron pair out to some electrophile, well, wouldn't it make sense that we would want to form the new bond at either the para position or one of the ortho positions when there's clearly extra electron density there? So this is another way of explaining the reaction mechanism by considering resonance delocalization, not just of the intermediate, but of the starting material itself. And I have 3 minutes left. That's going to be just enough for me to consider nitrobenzene. We can do the same type of explanation in the case of nitrobenzene. But now I don't think we're going to want intermediates that look like this. If, for instance, we move the electrons so as to, let's just try it. So as to put a minus charge over here, and a plus charge over here, that's no good. And I think you'll find there are others that look like that too, that put a plus charge right next to the nitro group. That's no good, because that's an electron withdrawing group, and you're asking that carbon that already has an electron withdrawing group sucking electrons away from it to bear plus charge. No, that's no good. So if we wanted to show other resonance forms of that particular compound, again, just the starting material itself, we would instead prefer to see structures that look something like this. Oh. Some people like to put circles around plus and minus charges. You can do that if you want to. I, for some reason, fell out of the habit a number of years ago. Couldn't really tell you why. But if you want to circle your charges, that's fine. So that one's fine because at least there's no plus charge right next door. And then you can find other resonance forms too. You can find, for instance, can think of at least 2 more, and there's probably others besides this. But we could put in the electrons like this instead. Whoops. And again, now there's going to be a partial plus charge here. But once again, at least that's not right next to the nitro group. And then I believe, yep, there's at least one other. You mentioned that you're recording these classes. Yes, they're on my YouTube channel, which is called R86 Chemistry. So every time I post a new one, you'll find it there. There should be a playlist for this class. So spring 2021, Chem 228. That's where they are. And I usually try to get them up at least within a day or so. But I can think of one other resonance form. We could also leave the plus charge there. And I'll end with this, by the way, and put the minus charge over here. That's also a valid resonance form. And so now, so far from putting a plus charge next to nitro, we're putting a minus charge there. That's a whole lot better. Of course, you're not going to get attack from that position because you're not going to put the new group right next to the nitro. You won't be able to get back to an aromatic ring. But if you look at resonance structures such as this, well, we see that it's the meta position that is the partial minus charge, because in so doing, at least we're never putting plus charge right next to the nitro group. Minus is okay, but not plus. Yes, but I don't want you guys memorizing that sentence. You're right, but the reason minus is okay is because it's those carbons that are going to donate electron density and form a new bond to that carbon. And what we find is with the meta-directing groups, lo and behold, it's best to put minus charge on metacarbons. You can in fact, I'm certain you can find other resonance forms that put the minus charge on the other metacarbon. Whereas with ortho-para-directing groups, we find there's extra electron density, extra minus charge, if you will, on the ortho and para carbons. So this is how Dr. Pennington explains this to his class, and he's certainly exactly right. He did not make that up any more than I made up what I told you about the intermediates. But my point is, and I'll end with this, you can explain why ortho-para-directing groups are ortho-para-directing and why meta-directing groups are meta-directing. Either way, you can consider resonance stabilization of the actual starting material itself, or you can consider resonance stabilization of the intermediates. Both give you good explanations for why the ortho-para-directing groups are ortho-para-directing and why the meta-directing groups are meta-directing. And you will need to know that. You will need to know that in order to understand the things you need to know for the exam. It's not going to be enough just to memorize sentences. Good. Well, I am out of time, so I guess I will see you all on Wednesday. Have a good day.